So next up we have Sid Hussmann, the CTO of Gapfruit, who will be talking about Showcase, microkernel OSs, TPMs, and WASM in IIoT devices.
2 years ago, Timothy Roscoe gave a Usenix keynote where he ranted about the lack of innovation in systems engineering. Well, times are changing. We can tell from the awesome talks we've seen so far, but also there are new topics rising up, like WebAssembly on the application layer. Then we have the industry enforcing zero trust principles with public key infrastructures and hardware root of trusts. Then we have communities such as the one around SCL4 that pushes the boundaries when it comes to security and assurance from the bottom up. In my talk, I want to demonstrate all these different awesome topics in one holistic product. First, here's our strategy. Product first. A little bit about my team. So my team started real-world product development using microkernels and capability-based security over a decade ago. In early 2018, I co-founded Gapfruit to bring the benefits of capability-based security to the business market. So with our first partner, we built an early version of Gapfruit OS with SCL4 on their IMX6 system on modules. Since then, we now run on HSMs, and we're now targeting the industrial IoT market with partners such as Bechtle. When it comes to industrial manufacturing, I want to talk about a specific use case. It is about connecting industrial equipment securely to the cloud. On the left, you see an industrial equipment that, in this case, a robot that has a multitude of sensors and actuators that kind of lack the cryptography or the computing power for basic cryptography for secure communication. So the gateway acts as a first line of defense towards untrusted network. Then it also may pre-process data before it's being transferred to the cloud for latency reasons. And since we learned yesterday, these apps also may transform from one protocol to another. So this gateway is kind of responsible for the availability, the integrity, and the confidentiality of the industrial equipment on the left. And in that order. So industrial equipment needs to produce always. So availability is key. Traditionally, these devices have been a pain to set up, a pain to develop applications for, a pain to maintain, and absolutely a pain to keep them reasonably secure. Let's change that. On the right, we see an operator that may analyze the fleet of devices for predictive maintenance. So WebAssembly started to address a need to run existing applications in the browser. Examples are Photoshop, AutoCAD, whole databases, or LLMs. The cloud natives were like, this is neat. What if we could, the container ecosystem has become so bloated. What if we could use WebAssembly instead? This is where WASI comes into play. It follows a capability-based model where you have to specify explicitly what access an app receives to specific resources of the system. Now, a few months ago, Docker announced the support of WASM Edge for their tooling and ecosystem. So what we get is a way to write applications like we were used to with containers, but with WebAssembly. And this is good on the cloud level because those WebAssembly apps are very, very small and are very, very quick to spin up. I mean, this movement on the application layer is awesome for us systems engineers. We can now use the same unmodified apps from the cloud folks on our awesome new operating systems. So after the announcement of Docker, we decided to support WASM Edge as well. So here is what we had to do. What we had to enable is LLVM and SPD log. Since we are a Genode-based system, we already have like a NetBSD type of libc and an POSIX shim. Luckily, we didn't have to enable libedit nor boost. So what are the ways to develop a WASM app for Gapfruit OS? What we see here is the structure of a Goa project. Goa is a tool from Genode Labs that enables application developers to port existing applications with different build systems and different programming languages to a Genode-based system. What we can see also is we have a subdirectory called HTTP server, which is one-to-one an example from the WASM Edge project, which is basically a web server written in Rust. What we can also see here, or what I want to point out, is an archives file, which specifies the SBOM of that app. So the SBOM is obviously WASM Edge and its dependencies such as LLVMs and stuff like that. What's also worth pointing out is this runtime file. This defines the topology of this subsystem. And in this case, it just starts WASM Edge with the app that we're building. And what it's also stating is the required resources and the provided resources. So I'm going to show a demo where we take this project and we're going to build it. We're going to test it locally on my x86 Linux machine. And then we're going to package it, sign it, and push it to a remote web server. So I'm going to adjust the version file to a new version. And I'm going to now change the Rust code so I can see that I did something with that code for demonstration purposes. And I'm going to just write on the console or reply when a package comes in. I'm going to run on the edge one day with whatever I've received. All right, so I'm going to now launch this in a minimal environment on Linux. And I'm going to test it by issuing a curl request. All right, computer says hello, and here it's going to print out. I'm going to run on the edge one day, and computer says hello. Nothing fancy. What I'm going to do next is I'm going to publish this app, which means I'm going to package it and I'm going to sign it with my development private key. So it issues cargo builds, and then it's already done. what I'm going to do next is I'm going to upload this app or this package archive to a remote server. So I can use it for later on this gateway, which is an ARM V8. All right. So what I want to talk about now is about Gapfruit OS. So I have two claims: 99% reduction of attack surface, and we enable mass provisioning of industrial IoT infrastructure. Now, before I want to go into detail of these two statements, I want to give a short overview of Gapfruit OS. So Gapfruit OS is a microkernel operating system with capability-based security. Given yesterday's talks, I would classify it as semi-dynamic. It is built with the Genode Framework, and from a business perspective, the Genode Framework lets us address business needs very quickly without risking the loss of the overall product. From a technical perspective, here are some things to point out. Well, for one, it supports multiple of kernels. One is SCL4, the other one is base HW, another one is Nova, and Linux. Now, for this IMX8 CompuLab gateway, we use base HW. But our vision is to replace that with SCL4 for advanced security and safety features. Now, what is also very awesome about Linux is there is some things awesome about Linux, which is the hardware support, right? How can we benefit from that? So Genode has a Linux device driver environment, which makes it easy to port existing Linux drivers to a Genode-based system. This lets us benefit from the vast hardware support that Linux has. Also, there are multiple runtimes and programming languages, but what I want to talk about now is the recursive system composition, where you can have a static system spin up a dynamic subsystem. So, and we extend this mechanism with a configuration management agent or multiple agents. And in the telco industry, in collaboration with our friends at Axiros, we implemented the TR369 standard, which enables us to integrate our system in existing telco infrastructure. And then we have support of that whole Microsoft Azure IoT ecosystem, which we're going to see in a minute. Now, I want to come back to this claim, 99% reduction of attack surface. So y'all probably wouldn't be here if you didn't know about some of the shortcomings of today's operating systems. But just to be on the same page, the Linux kernel consists millions of lines of code where each line is critical, each line you have to trust. So if you exploit something in a likely if you exploit a likely bug in a driver or in something inherently complex, such as a network driver, it's basically game over. But this attack surface is true for every part of this kernel. So how does the same vulnerable Linux driver behave on the Gapfruit OS? Well, since it's strongly isolated, and the guarantees are provided by the microkernel, and the capability-based model with limiting resource access, we can now argue if you exploit this driver, that exploit is contained in that component. And we can even argue that It does not sacrifice confidentiality nor integrity of the communication between a management agent and its cloud counterpart. When it comes to availability, our self-healing driver resilience system will detect a misbehaving component and kill and restart the component without any impact on the rest of the system. I have another demo for that. Okay. So what you can see here is on the top, I'm going to connect via SSH to my gateway, which is here at just a serial output. And I have a minimal bash environment. I can launch Vim and stuff like that, right? And then I'm going to attack the network driver. And we're going to see what happens. So the attack issued a page fault in the driver. However, the communication is recovered on SSH level. So I'm still connected until I'm not, but that was intentional. So what happens if I start a Linux system with the same vulnerable driver on this CompuLab device? So it takes a while to boot Linux. What I want to talk about, what we are doing now with this driver, it's essentially just another hop in our already untrusted network. So it doesn't have any impact on the trustworthiness of the gateway. So I'm going to now log into my Linux machine. I see, all right, this is a Debian Linux. And then I'm going to issue the same attack to that machine. And we can see it's a 5.10 kernel. And what happens? Kernel panic. So basically game over. Imagine happening that to thousands of devices at once. Here's my last topic. This is about TPMs. So TPMs are a hardware root of trust which provide a standardized API for different platforms. And we use TPMs for these topics, but what I want to talk about next is using TPMs for strong digital identity for authentication. This enables us to mass provision existing or IoT gateways. So I'm going to now talk how this process works in terms of physical provisioning before we ship the devices. So here you see the CA issuing a root certificate for a group of devices, a cluster, or a group of or a customer. We import this root certificate to Azure DPS. So any device that connects to Azure DPS with an intermediate certificate is granted access. On the gateway side, we create a private public key pair and in the TPM, and we issue a certificate sign request to the CA, and we prove to the CA that this key is generated on the TPM and is not exportable. Now, what did we have to do to enable TPM support on Gapfruit OS? Oh man, this was quite involving. We had to port the whole TPM to TSS stack from Linux. And this involved us to implement drivers as VFS plugins like the CRB driver for FTPM on x86 and the SPI driver for discrete TPM on the IMX8. And also for the SPI part, we had to enable TPM-TIS, which exports a VFS or a virtual file def TPM, which the TPM2 TSS stack expects. We also had to update OpenSSL 3 with the TPM2 provider. This enables us to create short-lived certificates from TPM-backed credentials. Now, how do we do this? On the top, we see the management agent, which is built with the Azure SDK. It needs credentials to authenticate itself to Azure. Now, what we see here is a simplified view of the TPM2 PKI keygen. This provides, this generates short-lived credentials and provides them to its clients. And for TPM2 TSS, that expects like a def./TPM0 as in Linux, so we provide that with this VFS mechanism. This kind of shows the power of the VFS mechanism that Genode provides. So essentially, TPM-TIS expects also a virtual file, which is provided by the SPI plugin. And here, then the communication goes to the TPM. So now we're going to come to the real demo of combining everything that I have talked so far. I will show how the different topics fit together. For one, there is an Azure Device Provisioning Service. And then we're going to see how we have a declarative desired state management system, and also how the devices authenticate themselves with TPM-backed credentials, and how that integrates with a PKI. And at the end, what I get is the deployment of the WASM Edge app that I built before and tested on x86, but it runs on this ARM device. I'm going to go through every step. So step one is the device is provisioned physically and is being shipped to the factory. It's being installed by the robot, and then we're booting it, and it connects over LTE to Azure DPS. On Azure DPS, we define an initial desired state that every device in my cluster should have. Once that gateway is connected to Azure DPS, Azure DPS will spin up a device twin for every device. So the device twin is a one-to-one relationship with the physical device. Azure DPS also initiates that initial desired state of that gateway. So given the desired state, the management agent will tell our package manager which applications and libraries it should install. The packet manager then goes to its depot, which is the web server that we saw before, where I published my packages. If everything is, or when everything is installed, the management agent makes sure that the data plane is being deployed, and it's and essentially the app that we built before is running, and then the robot can connect to that server, and we're all happy. All right, so how does that look? So on the right, we see the whole Azure stack. We have Azure DPS on the bottom. We have IoT Hub on the top. And here we have the output of a robot simulation. and here we have the serial output of my gateway. And this is all running on this. Now I'm going to define the initial desired state. I'm going to define the version that I want to deploy here, and the whole package name. And I'm going to set that initial desired state on Azure DPS. This will print some basic information about this enrollment group. And what we can see here is the attestation mechanism. And here it's a certificate-based and a root certificate reference. On the bottom, we see the initial desired state. We have a dynamic subsystem, and we're deploying my package that I built before. On the top, I'm going to connect to the IoT hub and see what it looks like. Obviously, this fails because the device hasn't booted yet, and DPS hasn't created its device twin. But we're doing this in a loop just to see, okay, at some point, this will be created. On the robot side, I'm also doing a script that tries to connect to the HTTP server in a loop until it's successful. On the bottom left, we see the serial output, and we see that the device is booting. And it gives me some information. It's starting the LTE driver, it's starting the credential manager, and then it starts the management agent, which connects to Azure DPS. We can see here connected to Azure IoT DPS, and the provisioning has been successful, and we can see that here, but let's not focus on that, because what we want to look at is that all the packages and their dependencies are being downloaded from the remote web server. All right, now we're waiting a bit. It seems like everything is installed now, and the WASM Edge is running. And I'm going to run on the Edge one day, which is today, and the robot says hello. On the top right, we see we can take now a look at the actual state of this gateway. And this reports the information of, let's say, a dynamic subsystem. And I can see what children it spawned and what RAM I've assigned and how much I've used and stuff like that. So this basically showed the process for one device, but this works for thousands of devices. So what I presented so far is a vertical breakdown of the whole system. Now it's time to address further improvements. So standardization takes time. And this is good and this is bad. But in the case for WebAssembly and WASI, this poses a risk for fragmentation because simple features such as sockets are not standardized yet, which means that different application runtimes or different WASM runtimes implement these missing features themselves. And that also means that the application depends on a specific application WASM runtime. And so what we also would like to explore is that whole development experience for application developers. And we're not quite sure how to do that because that is very hard to do. And we want to focus more on the operating system part and leave the application developers to other experts, such as Docker. And well, if we want to go down this route to enable like application developers to only focus on Docker and not on any of our system, we kind of have to support OCI images. So, and on the OS side, we want to improve the isolation guarantees that we get with SEL4 on this IMX8 ARC64 architecture. On the TPM side, we want to implement the ACME device attestation extension. This makes our lives easier for the whole physical provisioning process and the connection to a CA. Further, we're finishing the work on the TPM resource manager part. Thank you.
Thank you, Sid. We have probably time for one quick question. Okay, I have one. You talked about in your Gapfruit environment isolating the drivers that are reused from the Linux driver framework.
Right.
In my experience, Linux drivers are often tightly coupled with other components in the Linux environment. For example, a network driver has a lot of shared state with the stack. How do you isolate these two?
So, so there are two parts. So one part is about the dependencies on the kernel interface, which is posed as the device tree, right, from Linux. And what Genode did is to make that work, streamline that part of work and make that as easy as possible. The other part is with our client-server architecture, we define, okay, a multiplexer is more trusted when it comes to availability, but also for policies. And we designed the system in a way where the driver would connect to the server. So the multiplexer is not dependent on the driver because that's complex and code and which is buggy and stuff like that. So in this case, we have a multiplexer that is able to handle like these short outages of the drivers. Does that answer your question?
Yeah, somewhat. Thank you. Okay, we have a break now, but come back at 11:30.
Thank you.
Thank you.